Hello, everyone. It's a true honor and privilege to have this opportunity to give a plenary at ICASSP, even virtually. It really feels like a highlight of my career. I'd like to thank the organizers, Anna and Isabel in particular, for inviting me to give this talk. Of course, I was very much looking forward to seeing you all in person in Barcelona, which is one of my favorite cities, but very thankful to everyone involved for giving us an opportunity to meet and exchange ideas, even under these difficult circumstances. Once again, the Signal Processing Society has shown how creative and determined it is. Not even COVID-19 can stop ICASSP from happening. This ICASSP program is especially spectacular, so it's really a great honor to be part of it in its new innovative form. Actually, I've been coming to ICASSP every year since ICASSP in Turkey in 2000 when I was a PhD student. And to me, the IEEE Signal Processing Society is really my home. So it's very special for me to be able to commemorate my 20th ICASSP by giving this talk. Before I begin, I'd like to wish everyone in the community and their families lots of health and wish us all to be able to meet again soon in person. Today, we live in a digital world with extraordinary amounts of data being generated on a daily basis. What I'd like to share with you today are some ideas that we and many others have been working on to acquire and process signals using much less resources than what is used today, and we'll do that by relying on basic ingredients of signal processing, exploiting models, exploiting structure, and taking into account the specific desired tasks. Now, what I hope to show you today is that this leads to new ways of sensing information and to interesting new technologies that can have an impact beyond engineering in different areas of science and medicine. So data today is being generated at exponentially growing rates, and this creates unbearable demands on the sensing devices, on storage, on processing devices, and on communication systems that all have to be able to deal with these large amounts of data. In fact, there are more than 3 million data centers worldwide just to store this data, like we see in this data farms over here in Finland. This also leads to extremely high power being consumed on acquiring and processing these large data sets to such an extent that, as we see in this table over here, the energy consumption of the IT industry is larger than many big countries such as Russia and Japan. In fact, by 2022, Cisco predicts that the internet traffic will approach a zettabyte, which is 10 to the power of 21 bits. So that's a huge number of bits. The question is whether we really need all of this data for the tasks we're actually interested in solving. What we're going to claim in the talk today is that there's a lot of redundancy in data that is not being exploited today in the acquisition process. So as one example, we can look at medical imaging devices that today tend to be large and bulky and often lead to high radiation and also can take a very long time to scan. Now, one of the reasons that this happens is because these technologies acquire a large amount of physical data, typically from multiple sensors, as we see here, for example, in this plot of ultrasound data coming out of this probe. But at the end, in order to make different decisions and for diagnostic purposes, what is used is not all of this data, but actually this data is projected down to a series of images, and only those images are used for diagnostics. As another example, smart cities or autonomous vehicles collect a large amount of information from many sensors and cameras, but at the end, this is all distilled to very specific decisions. A final example are deep neural networks, which we know work extremely well when they're trained on huge amounts of training samples. But on the other hand, we know that children can perform, for example, classification using only very few examples. So these examples all illustrate that we seem to be acquiring much more data than is actually needed for solving the tasks we're interested in. And this leads to the question of whether we can acquire only the information that we actually need. Now, when we talk today about data, we're typically referring to digital data, by which we mean streams of bits that are processed by various mathematical algorithms. And this gives our digital devices the advanced capabilities that they have today. However, in reality, many of the signals we actually want to process are physical signals, such as music and speech, and these signals are continuous in time and in amplitude. Therefore, in order to be able to process them digitally and enable the advantages of digital processing, we first have to convert them to bits, and this is achieved by sampling or analog to digital conversion. Analog girl in a digital world. So the song by Judy Gorman, who's a pop singer, nicely captures for us the essence of sampling. Today, more and more of the processing is being done by digital devices. However, the world around us is analog. Therefore, in order to be able to enable digital processing, we have to convert the continuous time signal, such as speech, for example, into samples. And this is done by using an analog to digital converter. Now, what the ADC does is it first samples the signal at certain points in time, and then it represents these sample values by a sequence of bits. Now, today, the sampling rate used in essentially all ADCs follows the well-known Shannon-Nyquist theorem that states that the sampling rate has to be at least twice the highest signal frequency. In fact, today, when we look at acquisition systems, they're built in modular blocks. So to show this, suppose we want to acquire an ultrasound image. What we'll do is we begin by transmitting and receiving an ultrasonic pulse. And then after the pulse is received, it is sampled, and the sampler will sample it at the Nyquist rate, which in this case can be quite high. The samples are next quantized, and this is done typically based on the well-known high rate limit that dictates that for each bit we add, we're going to gain roughly 60 dB in quantization SNR. The bits are then digitally processed, where only at this point is the desired task of the system taken into account. So for example, in the context of ultrasound, typically the task is to process multiple signals received in multiple elements, and the goal is to beamform this data to form a directional beam in a certain direction, and we do this by applying adaptive weights. Now, after this processing is performed, we obtain an output image, and this image that we see over here is basically a projection of the continuous time data that we actually acquired onto a low-dimensional space. Now, in the standard approach that is followed in essentially all acquisition devices, each of these blocks in the acquisition chain is designed separately, and it's designed based on local optimality criteria that are relevant only to that block. And they do not take into account the other system property, okay, such as properties of the signal beyond bandwidth or the specific task that we're actually interested in. Now, this approach leads to high demands on the individual blocks, and in particular on the sampling and quantization rates. So today, we tend to use signals that have higher and higher bandwidth, and this is in order to deliver higher rates of information, for example, in the context of communication, or to obtain better resolution in different imaging applications. Now, as the bandwidth grows, the Nyquist rate and quantization rates will grow and become very high if we don't take other properties into account. Now, high rates are very difficult to execute in practice in terms of hardware. They also lead to large digital databases that have to be processed, stored, and transmitted. In the context of medical imaging, which we've been working on a lot recently, high rates translate to high scanning times and to large radiation dosage. So at the end of the day, these ADCs that are key components in any digital device lead to many system bottlenecks. Now, what we're going to suggest in our talk today in order to overcome these data management issues is to fundamentally change the way we design systems. And we're going to do that in such a way that all system components are designed jointly rather than being optimized separately, as we saw before in standard acquisition systems. In this joint optimization, we're going to take into account both the desired outcome or the task, and also the structure of both the signals and the system. And what we'll see throughout the talk is that by exploiting the structure and the task, we can reduce the rate substantially and also very often improve system resolution. Furthermore, we're going to see that using these ideas of joint design and exploiting the task and the structure can also be used not only for acquisition, but also in deep networks to develop model-based interpretable deep learning methods that in some sense nicely reconcile models with learning from data. So what we're going to show in the talk today are various different advantages of this joint design. So we'll see that they lead to compact devices, for example, a wireless ultrasound probe that we're going to show. They lead to fast and quantitative MRI, to very efficient wideband sensing, to cheap and high resolution radar devices, to very efficient communication using MIMO systems, to new technologies such as joint radar and communication systems. We'll also see that they lead to super resolution, for example, in microscopy and ultrasound. And finally, as we said, we'll see that they could lead to interpretable deep networks. That was the main idea that we're going to see today throughout our talk. And now I want to give a high-level outline of the rest of the talk. So basically, this talk is going to be divided into 3 parts, where in each of the parts we'll focus on first structure, then task, and then the models. We're going to start by discussing how we can exploit structure to reduce rates by introducing the sampling paradigm, which is basically a combination of compression and sampling. And we'll see different applications to wireless ultrasound and to radar. We'll then consider task-based sampling and focus on specific tasks of power spectrum estimation and quantization. And we'll see that this can lead to new ideas in cognitive radio and super resolution, as well as efficient communication systems and distributed learning systems. Finally, we'll end by discussing how we can integrate these ideas into deep networks so that we can build new classes of deep networks that can take the physics and known models into account. So we're going to begin by considering how we can go from sampling to sampling by exploiting structure. Now here on the slide, what you see are some of the systems we actually built in the lab following these ideas, so that you see that these are not only theoretical ideas, but can actually lead to new systems. Let's start by seeing some examples of structure in various signal processing problems. One type of structure that we looked at originally is a multiband signal, in which several narrow bands are transmitted over a wide bandwidth, but the carriers are unknown or changing over time. Now we can of course treat such signals as band limited to Fmax and sample them at the Nyquist rate related to Fmax, but that is of course wasteful since a large part of the spectrum is unoccupied. And if we sample at Fmax, we're basically accommodating signals like the signal we see over here, which occupies the entire bandwidth, while our signal will always have structure that is not exploited in that case. Now, the same model that we see over here for communication can be used in different imaging problems where we use multiple frequencies for imaging, like hyperspectral imaging or multispectral CT. Another model that appears, for example, in radar and ultrasound imaging, and in fact in any time of flight imaging, is the model of a stream of pulses. This model was first suggested by Vetterli and his colleagues in a beautiful series of works referred to as finite rate of innovation. Now, in this model, what we receive is a stream of pulses where what we don't know are the times of arrival and the amplitudes. So, for example, in the context of radar, we send a known pulse through the transmitter. It then hits different targets, such as these airplanes over here. And at the receiver, what we're going to get is a reflection every time it hit a target. So if we could figure out these times of arrival, then we can figure out the distance to the targets. And from the amplitudes across several pulses, we can figure out the velocity. Now, these signals today are sampled at the Nyquist rate, which is the bandwidth of these pulses. But that can be the same as an arbitrary signal, like the signal we see over here. So we're not taking into account the specific structure of a stream of pulses. The very same model appears, for example, in ultrasound, where we send a pulse through the ultrasonic probe, and what we view are reflections of this pulse as it propagates through the tissue. So in this case, we want to somehow take into account this stream of pulses, and if we could do that, then we could get away with using fewer samples and end up with higher resolution. Now, in fact, the ultrasound problem we saw before is actually more complicated than the radar problem, and that's because the environment is very noisy, and also the imaging is done in the near field. So in practice, we use a probe that has multiple elements, typically somewhere between 128 and 256 elements. The signals are then received in all of these elements, and then they're beamformed in order to increase SNR and resolution. Now, this beamforming in practice is done in sample data on a very fine grid so that we could be able to apply these very fine delays that result from the fact that the signal is going to be received at each element with a time delay that depends on its distance. Okay, so we have to sample at a very high rate, but this of course requires both high sampling rates and very high processing rates, which is very difficult to do in practice. So the difficulty here is not only reducing the sampling rates, but actually being able to perform this nonlinear beamforming on sub-Nyquist samples without having to interpolate to a high Nyquist grid. And what we're going to see later on in the talk is that we can actually do this by a process which we refer to as compressed beamforming. So we could both sample at low rates and do the beamforming at these compressed rates. And what this will enable is it will allow us to reduce the size of an ultrasound machine without harming its resolution. It would allow us to increase frame rate, which is very important, for example, in cardiac imaging. It will pave the way to 3D imaging. And one of the nice applications that we'll see is that it can allow an entirely new ultrasound scanning experience where instead of having a big machine, we're going to be able to scan only with the probe and use a simple tablet or a cell phone in order to do the recovery. So it turns out that all of these examples that we've seen and many others can actually be treated in a unified mathematical framework, which is referred to as a union of subspaces model. So this model is quite simple. It assumes that our unknown signal lies in some low-dimensional subspace, but that a priori we don't know which low-dimensional subspace. So we have many options of subspaces. In fact, we can have possibly an uncountable number of subspaces. And the only thing we know is that our signal lies in one of them, but we don't know a priori which one. Now, the importance of this model is that, first of all of the examples we've seen before and many others can be described within this model. And what we can show is that in all of these examples, the minimal sampling rate needed is the rate associated with the sum of two spaces in the union, irrespective of the number of subspaces we have. And this is really what paves the way to Sub-Nyquist sampling. So the next step is providing an explicit hardware design that will achieve this minimal rate. And this is provided by the Xampling paradigm that we've developed, which leads to concrete system designs. And in fact, the boards that you see here on the slide are all developed based on this Xampling paradigm. So to reduce the rate, what we suggest is the counterintuitive idea that we first have to alias all our data prior to sampling. So we're going to take all those options of subspaces that we have and linearly combine them so that we could project them onto one low-dimensional subspace and then sample at a low rate only that low-dimensional subspace. Now, in practice, in terms of hardware, this aliasing that we talked about is performed by mixing with periodic functions. And we know that periodic functions in time will look like a delta comb in frequency, so that mixing with them will be aliasing in the frequency domain. So that if we start with this multiband signal, after multiplying with the periodic function, we're going to get aliasing in frequency so that the signal appears all over the band. We'll then low pass it, so we only take the low pass regime, which can of course then be sampled at a low rate. So the analog pre-processing is performed by this mixing function. We then acquire the signal at a low rate using a standard low rate ABC. And then in order to recover, we're going to use ideas based on compressed sensing to localize the correct subspace. So what we can show is that this type of sampling, which again is performed in these analog boards we see over here, has various different optimality criteria. So we can show that from all Sub-Nyquist methods, it achieves the minimal mean squared error since it achieves the Cramér-Rao bound. And we can also show that in the context of communication, it will minimize the worst case capacity loss over a wide class of signal models. So this type of sampling has various forms of optimality from all Sub-Nyquist sampling methods. Now, after we've sampled at the low rate, in order to recover the correct subspace, we rely on ideas of compressed sensing. So this slide gives us a very compressed version of compressed sensing, where essentially the main idea is that if we have a sparse vector x, meaning a vector x that has a small number of non-zero values, we can recover it from a short measurement vector y, as long as this measurement vector is taken so that the measurement matrix looks like a random matrix, and that means that every element in Y is going to be a linear combination and essentially a random linear combination of all elements of X. And what compressed sensing theory tells us is that we could recover such sparse vectors without knowing where these non-zero values are very efficiently using various different efficient computational methods. So in our context, these measurements are going to be the samples after we use the Xampling paradigm, and the vector X will indicate the correct subspaces. The original compressed sensing is a linear theory. In order to address many of the practical and clinical problems we encountered in practice, we had to extend it in many ways. So over the years, we and many others have extended the basic compressed sensing principles to different nonlinear problems, which is particularly important, for example, in optical problems such as phase retrieval, to problems with multiple images that share similarities, which we used, for example, in MRI, to tracking, which is very important in blood vessel tracking, like in ultrasound, and to sparsity in the statistical domain. Furthermore, there have been many really beautiful works in the past few years on how to use deep networks to recover from compressed samples rather than the optimization methods we mentioned before. The first work along these lines is the well-known LISTA paper, which suggested a model-based network to recover sparse inputs. And this is based on the concept of unfolding that we'll discuss in detail at the end of the talk. In the past 2-3 years, there's also been a really beautiful series of works on how to use different network architectures to recover from compressed samples using various forms of learned structure that are not necessarily sparsity and do not necessarily have to be known in advance. So combining the analog and digital ideas we presented until now leads to a general framework for Sub-Nyquist sampling based on structure that can be applied in a wide variety of systems. So here on the slides at the bottom, you see some of the prototypes and systems we've developed based on these ideas. And in our books on sampling theory and compressed sensing, we go into much more detail, both on the theory behind these ideas and on the ideas behind the hardware. So with that, I want to move on to show some applications of this framework and to show you that despite this very famous quote of Albert Einstein, in theory and practice are the same, in practice they are not. We'd like to show you that if you take the practice into account in developing the theory, then the theory can actually work pretty well in practice as well. So the first application I want to show is to ultrasound imaging. And what we've been able to show in this context is that we can actually acquire ultrasound images using only 4% of the Nyquist rate in every channel. And we actually don't even have to use all of the channel. Now, this leads to several interesting clinical applications. So first of all, it paves the way to 3D imaging, which today is limited by the high data rates. It allows a high frame rate, for example, for cardiac imaging. Since we have less data, we could process it quicker. And finally, I think the coolest application is a wireless probe that we've developed based on these ideas. So today, ultrasound systems are large, bulky systems where the acquisition is done by a probe, which is totally analog. The data goes through the analog cable into the system, and only there is it sampled and processed. Because now we could sample at a low rate, we can actually do all of the sampling within the probe, which means that we don't need the cable. All we need is a probe. In fact, we don't even need a machine. The low rate data could then be transmitted over any standard Wi-Fi device. It could be transmitted to a tablet that the doctor is holding in his hand to recover the image. And at the same time, the data could be sent to the cloud for more elaborate processing and, for example, to use deep networks. So what I want to do next is show you a quick demo of a prototype we've developed in our lab.
Demonstration of a normal
so this is Dr. Shai Taiman Yelden, a cardiologist we are working with. And he's scanning my former student Regev in our lab using our device.
We can see right now the left ventricle, the right ventricle.
The cable is used just for power purposes. All of the data is being transmitted wirelessly to the local machine,
we can see
to a tablet, and to a remote machine via the cloud.
We can see that actually there is good ventricular function and there is no pericardial effusion. The picture itself is very good, very crisp, and we can demonstrate very nicely this subject's heart.
Okay, now you see him scanning directly to a tablet. So one of the really nice aspects of this wireless probe is that it enables access to data which previously was simply not available. So before, we already got an image out of the machine, but now we have access to the actual raw channel data that we could go ahead and process in more elaborate ways rather than just performing beamforming. So for example, one thing we suggest to do is to use trained beamforming weight. So we use deep learning, not for end-to-end learning, but only to tune the beamforming weights. And we do this from training data. So this is work that was done in collaboration with TU Eindhoven and Philips. And we showed that we could get images with much better contrast and resolution than standard machines by simply choosing these weights adaptively. And this was enabled by the wireless probe that now gives us access to channel data. In fact, this ability to sample and process channel data opens the door to many exciting new clinical applications that previously were simply not possible because all we had was an image. So we actually began a clinical forum at the Weizmann Institute, which is dedicated to this topic, with many leading clinicians in Israel and in the Boston area, where what we're doing is examining various new clinical applications that are enabled by channel data processing. So I think this is a really nice example of how new technology can not only lead to more efficient systems, but can actually enable entirely new clinical applications by enabling new views on the data that were previously not possible. The very same ideas we applied to ultrasound, we could apply to radar, and this leads to various different compact and power efficient radar systems. So many of these ideas are summarized in our recent book on compressed sensing in radar, which was edited together with Antonio Di Maio and Alex Chaimovich. So let me just show a very quick video of some of the ideas we've developed in the context of radar, and they're very similar to what we've seen in the context of ultrasound. So we know that in radar, the basic trade-offs are between resolution and bandwidth. Another basic trade-off is between dwelling time, the time we look at a target, and the velocity resolution or the Doppler resolution, and finally between the number of elements and the spatial resolution. So using this idea of sampling, we could actually break all of these trade-offs. So here you see the sampling board we've developed, the Sub-Nyquist radar board we've developed, very similar to ultrasound. What it does is, instead of looking at the entire bandwidth, it could receive only a small set of narrow bands, and from that still get all of the information, even when we have large clutter and large noise. And here you're going to see a delayed Doppler map that we could recover, so even very close targets can be recovered, although we used very small bandwidth. Now, this also paves the way to cognitive radio, where now our radar system could coexist with communication systems, because instead of using a wide pulse, we could use only narrow bands wherever there's vacancies in the communication channel. So this leads to very efficient cognitive radar systems. Now we could do the same thing to reduce time and target. So instead of sending all of our pulses in one direction, we could send random pulses in different directions and get very good Doppler resolutions in different directions in the time which traditionally we would get only one direction. So here we see this idea where we develop two very high resolution maps in two different directions. At the same time, we would normally have only gone in one direction. And finally, we could use the same ideas to reduce the number of spatial elements, so we could use much fewer elements and still get very good resolution. In fact, we get even better resolution than a Nyquist system because our recovery is now done in a more efficient way. Currently, we're exploring applications of these ideas to automotive radar, where cheap, fast scanning and coexistence with communication channels is very important. And in fact, later on at ICASSP, we have a demo that shows these ideas in one of the show and tell sessions, so we encourage you to go see it. Until now, we have seen how we can exploit structure to reduce sampling rates and design compact systems. What we want to discuss next is how we can exploit the system task, even when there is no structure, in order to reduce the rates. Now, in many applications, we sample a signal, but what we're interested in is not recovering the individual signal, but rather in recovering some function of the signal. What we want to discuss now are some examples of how we can exploit these types of tasks to reduce sampling rates, and how this can again be used to introduce some interesting new technologies. In particular, we're going to look at problems where the task is, for example, recovering the signal power spectrum. And this is joint work done with Gert Lewis and Debbie Cohen. We're going to look at the interplay between quantization and sampling, which is joint work done with Alon Kipnis, Andrea Goldsmith, and Tzachi Weitzman. We're going to look at tasks related to communication, such as channel estimation, which is work done with Neil Schlesinger and Miguel Rodriguez, and at sampling sets of signals, when what we are interested in is in their joint support. So in all of these applications, we don't want to recover the individual signals, but rather some joint function, and we'll see that this is actually easier than recovering the signals themselves. So we're going to begin by looking at power spectrum reconstruction, where we sample signals, but what we're actually interested in is recovering their covariance function. And this appears in many different signal processing problems, such as problems where we care about support detection, like in cognitive radio, in different array processing problems, for example, direction of arrival estimation, in financial time series analysis, and in imaging, such as optical imaging, where we only care about the brightness in the image, which is proportional to the variance. So the sampling question that arises in this context is, what is the minimal sampling rate at which we need to sample the signal in order to estimate its covariance when we assume that the signal is Y10 stationary and ergodic? Now, in the past few years, there have been actually really nice papers that looked at this problem and considered specific sampling mechanisms in the asymptotic regime. What we want to do here is take a more general approach to this problem in order to be able to characterize general possible sampling sets. And interestingly, it turns out that substantial rate reduction is possible even for finite rate sampling sets. So before we go into the actual results, I'd like to try and give some intuition as to why should we be able to reduce the sampling rate when all we care about is the covariance, even though we're not assuming any particular structure on the input. Suppose we have a set of sampling points like we see over here, where the set is very sparse, okay? So it's not dense enough to recover, for example, a band-limited signal, since the samples here will not be at the Nyquist rate. Okay, so this is not a sufficiently dense set. But when we're looking at covariance estimation, what we care about are not the sampling points themselves, but rather the difference set, the differences between these points. And that's because the covariance of a stationary signal will depend only on the difference set. So we could come up with sets that are quite sparse, but their difference set could actually be dense, and therefore, although we cannot recover the signal, we'll be able to recover its covariance. So we can make this more precise and show that it's possible to create sampling sets that have a density or a Berling density of 0, meaning their sampling rate is 0, but their difference set will have a Berling density of infinity. So for this to be true, we need two conditions to be satisfied, where the formal conditions are written below in this theorem, but intuitively what these conditions say is that the density of the set has to go to 0 slower than the square root, like is illustrated over here. But there should be enough distinct differences so that if we look at the difference set, it will grow like the square of the size of the sampling set. So any set that will satisfy these conditions will be able to recover the covariance from a 0 sampling rate. Now, these are still asymptotic results. The question is whether they are sets with a finite rate that will still satisfy these conditions. And the answer is that there are many possible such sets. One of them is multicoset sampling. So in multicoset sampling, we take the Nyquist grid, we divide it into blocks of size n, and from each set of size n, we're going to choose only m points. So this is the same as taking m samplers, each one at an nth of the Nyquist rate, where each one of them has a different time delay. Now, if we want to be able to recover the signal itself from these samples, we're going to have to take n channels so that overall we're back at the Nyquist rate. But what we can show is that if all we want is to recover the covariance, then we only need square root of n channels. And this is the square root of n savings that we alluded to before. So next, I want to show an application to cognitive radio. And before I do that, I want to point out that there's many other possible sets that we can use, such as the Xampling paradigm, which is much more convenient for practical samplers, in particular in the context of cognitive radio. And in fact, if we use the Xampling sampler, we can show that we can use it not only to estimate the data and its covariance, but we can also use it to estimate the cyclic spectrum, which helps improve robustness in practical problems. So let's turn now to see an application of these ideas to cognitive radio, where the idea in cognitive radio is to build smart radios that can sense the spectrum and discover channels that are not being used, even though the spectrum band is all licensed. Now, the advantage of this approach is that it could allow to overcome the spectrum congestion and increase channel capacity. Now, of course, there are many difficulties in employing cognitive radio, but one of the main issues is how to scan wideband spectrum continuously with a cellular phone. Now, since our approach enables discovering these white holes efficiently, meaning places where there's no signal right now from low-rate samples, this can provide a solution to the sensing problem in cognitive radio. So what I want to do next is show a demo that we've developed for cognitive radio. And this we're going to see in this next short movie over here, where more details could be found in our magazine article on this. So this is the actual card that we've developed. It could sample at 6% of the Nyquist rate. So instead of sampling at 6 gigahertz, it will sample at 360 megahertz. And what you're going to see now is the actual card in real-time operation, where at the top channel over here, you're going to see rapidly changing signals. This is the alias spectrum, since we sampled at a low rate, and this is going to be the signal recovery or the spectrum recovery. And what's nice is that this is very robust to noise. It doesn't depend on any specific properties of the channel or of the signal, and it could be used whether or not the signals are narrow or wide or almost independent of the noise level. An entirely different application is super resolution microscopy. So we know that optics is extremely convenient to use for microscopy. However, it is limited by the well-known Abbas diffraction limit that says that we cannot see details that are smaller than half the wavelength used for illumination. So in the optical regime, we can see, for example, cells and bacteria, but we won't be able to see proteins and small molecules. In 2014, the Nobel Prize in Chemistry went to the really nice idea of super resolution optical fluorescence microscopy, where in order to take one super resolved image, the idea is to take thousands of exposures, where in each exposure we control the fluorescent molecules, so only a small number of molecules are actually fluorescing, and therefore we could just go ahead and localize them, and then sum over all images to get one super resolved image. This leads to very good spatial resolution, but it does it at the expense of the temporal resolution, since we need many frames for one single image. The question is whether we could get both high temporal resolution and high spatial resolution. So to do that, we rely on these ideas of correlation microscopy, since to see these brightness images, it's basically enough to just recover the variance, and we know that we could recover variance from a small number of frames. So what you see over here is a comparison of our method, which we called SPARCOM, which relies on these correlation ideas, and we compare them to STORM, the method behind the Nobel Prize. And we see here that from a very small number of frames, 2 orders of magnitude less frames, we could get better resolution than we get in STORM. Here we see a cavity that we can see in SPARCOM with 50 frames, and we don't see in STORM even with 500 frames. So for much less frames or much quicker, we could get much better resolution. Now, we've also extended that to a deep architecture, to a deep network, by unfolding the ideas of SPARCOM, and this enables SPARCOM to perform even better, quicker, and does not rely on knowledge of the point spread function. Since we can now do super resolution very quickly, this paves the way to live cell imaging, and we're now looking at using SPARCOM to investigate various biological processes. And in particular, in collaboration with a group of Professor Gilad Daran, we're looking at imaging T-cell receptor in live cells, which was not possible before, and these play a very important role in the immune system. We're also exploring the use of these ideas to improve ultrasound imaging. Now, of course, in ultrasound, we can't rely on fluorophores, but we could rely on the fact that today, very often in ultrasound scans, one uses contrast agents, just like is done in other imaging modalities. So in ultrasound, these contrast agents are microbubbles that are injected into the bloodstream. And when we image in a fixed plane, these microbubbles hit the plane in a stochastic fashion, so that mathematically this is very similar to what we've seen before with the fluorophores. So in this context, we refer to our method as SUSHI, Sparsity-Based Ultrasound Super Resolution Hemodynamic Imaging. And in fact, the first time I presented at an ultrasound conference, someone got up and said that it's a very fishy method. And indeed, it does look fishy because we get really good depiction of blood flow, which we couldn't see before. So we're now exploring several clinical applications of SUSHI, in particular to try and monitor the disease in Crohn's disease without having to go through invasive procedures. And we're also exploring the use of this for breast cancer detection. The next task we want to consider is quantization. So until now, we ignored the quantization effect and we only looked at the sampling effect. But we know that in general, quantization is always going to introduce distortion to the signal. And therefore, the question is, since we have distortion anyway due to quantization, do we still really need to sample at the Nyquist rate, which is the rate that allows perfect recovery, assuming we don't have any additional distortion? More specifically, when we look at sampling theory deals with sampling in time, but not in amplitude. On the other hand, quantization theory or rate distortion theory or source coding theory looks at quantizing the amplitudes, but does not look at sampling in time. So what we would like is to develop a theory that unites the two and gives us a distortion theory for continuous time signals. And then using that theory, we'd like to know what is the minimal sampling rate to achieve the optimal distortion. So this is joint work that was done together with Andrea Goldsmith and Alon Kipnis. And to be more specific, what we want to look at is rate distortion theory for analog inputs. So the standard rate distortion theory looks at the problem of optimizing over all encoder-decoder pairs at a given bit rate, the minimal distortion we can achieve from a discrete time input and a discrete time output. On the other hand, what we're interested in is asking a similar question, but now the input is going to be continuous time, the output is going to be continuous time. We're again going to have a fixed bit rate and optimize over all encoder-decoder pairs, but we're also going to look at the sampling function. So first we're going to have a fixed sampling rate and ask what is the minimal distortion we could achieve. But then the next question is, given that minimal distortion, what is the minimal sampling rate we need in order to achieve that distortion? So first we were able to derive these optimal analog rate distortion curves. And once we get these curves, we can use them to analyze the minimal possible sampling rate. So in particular, we could look at what the minimal sampling rate is to get this minimal distortion, assuming different input functions. And here we compare that minimal sampling rate as a function of the bit rate for these two inputs, which are different. And we see that we could, for many bit rates, sample below the Nyquist rate and still get the minimal distortion. So we're not incurring any additional distortion due to sampling. What's also interesting is that we could now get finite sampling rates for non-band limited inputs. So this green input over here is the Gauss-Markov process, and we see that for every given bit rate, there's a finite optimal sampling rate at which to sample and achieve the minimal distortion. In practice, however, achieving the optimal rate distortion curve requires vector quantizers, which are impractical to implement in standard systems. In fact, most ADCs rely on simple scalar quantizers that yield performance far above the rate distortion curve. So the next question we wanted to address is whether we can exploit the underlying task we are interested in order to simplify the quantizer, namely to develop hardware-limited quantizers that achieve optimal performance. We consider this problem in the context of communication, where often there is a specific task, such as channel estimation or bit recovery. We therefore propose to use simple scalar quantizers, but to allow for analog combining before the quantization. Namely, we're going to linearly mix the input to be quantized, similar to the idea in compressed sensing, but here we're doing this not to reduce dimensionality, but rather to reduce quantization error. What we suggest is to jointly optimize the system consisting of the combiner, the quantizer support, and the post-processing to minimize the error in various communication tasks. It turns out that in this way, we can actually use very simple scalar quantizers and achieve the same performance we would have achieved if we were using vector quantizers. We next went ahead and applied these ideas to massive MIMO communication, which has been gaining a lot of interest for next generation cellular systems. The drawback, however, is that it requires very expensive hardware to sample, quantize, and process the data from all the antenna elements. Now, there's been a lot of work that considered analog combining in this context to reduce the number of RF chains. In fact, in some of our earlier work, we developed a general optimization framework that allows optimizing the analog combiner for different communication tasks. There's also been a lot of work on using low bit or even 1-bit quantizers in each RF chain in order to reduce the cost of the hardware in this context. The typical approach is to apply a 1-bit quantizer and then try to compensate by appropriate post-processing based on different approximations of the resulting mean square error. However, this will of course lead to performance loss. Now, using our general approach, we can now combine the two and introduce the precoder both to reduce the number of chains and to reduce the number of bits. And it turns out that by using this approach, we can actually develop systems that perform as well as the system that we would have gotten with full RF chains and high bit rate. And this performs better than the previous method suggested for this problem. Now, until now, all the systems we introduced require knowledge of the channel statistics in order to optimize their performance. As a next step, we relied on the magic of deep learning and used this to compensate for unknown channel statistics. Now, we do this again in a model-based fashion. So rather than arbitrary end-to-end learning, we keep the structure of the quantizers, where we have a precoder, simple scalar quantizers, and post-processing. But each one of these blocks is now going to be optimized based on our task-driven metrics. And it turns out that we can then approach the ideal performance even though we don't know the channel statistics. So next I want to show a demo we developed in our lab that illustrates how we could do this in practice. So what you see here is a demo of a massive MIMO systems that's not so massive. Here we look at 8 chains that we reduce using our ideas. And what you see here is that we could actually build this hardware in practice as well, where we reduce both the number of bits and the number of RF chains and still get optimal performance. And those of you interested can see this in our demo in one of the show and tell sessions later on at ICASSP. Now, right now, in order to be able to do the precoding, we have an additional piece of hardware that does this analog precoding. What we've been exploring recently, and we'll also be presenting at a talk at ICASSP, is using Metasurfaces for this purpose, where basically we could change the response in each one of the antenna elements by changing the current. And in this way, we get the precoding built into the antennas. And this is joint work with a group of David Smith at Duke. We've also been applying similar ideas in radar in order to reduce the number of antenna elements needed for radar detection. And again, we have a demo of a radar system that we've developed for this context. So here you see an antenna array where we only are going to use part of the antenna elements using these ideas and show that in the context of automotive applications, we can still get very good tracking of moving targets. And this is the demo that you could see later on in the show and tell at ICASSP. Now, since we showed that we could get very good very efficient communication systems from a small number of elements and efficient radar systems, we can now combine them onto a single platform where part of the antenna elements are used for radar and part of the antenna elements are used for communication. And this is again another demo that we have later on at the show and tell session at ICASSP. And what we show is that on the same platform, we could do both radar and communication without harming the performance of either one of them. So here you see the actual system, the transmitter and the receiver for both radar and communication. A final application of task-based quantization that we've begun exploring is to federated learning. The idea in federated learning is to train algorithms using multiple decentralized devices without sharing the local data. What is shared is only the weight updates. Now, this enables both efficient learning and also ensures privacy since no data is shared. However, the communication costs in sharing the weight updates continuously is quite high. What we suggest, therefore, is quantizing the weights for the task of learning. And what we've shown is that we could quantize down to a low number of bits while obtaining the same overall learning performance. And we have a detailed paper on this later on at ICASSP as well. The final joint task we would like to consider is beamforming, which is used in ultrasound and radar to form images from multiple antennas. So in general, in beamforming, the image quality is determined from the beam pattern, where the main lobe width will give us a sense of the resolution, and the peak of the side lobe will give us a sense of the contrast. So the question is whether we can create the same beam pattern with less elements in a single image. And of course, in general, this is not possible, but what we show is that we can actually do this if we add a convolution process before we actually form the beam pattern. And this is what we refer to as convolutional beamforming. So instead of the standard delay and sum beamformer, we introduce the convolutional beamformer, where we delay the signals, we convolve spatially, and then sum them up. And it turns out that this leads to a much better beam pattern. So more specifically, we can show that the resulting beam pattern is the same beam pattern we would have gotten if we looked at the sum co-array, meaning the sum of the array with itself. And this is in fact a very similar idea as what we get to with sparse arrays for correlation processing, which has been gaining a lot of interest since the really nice work of P.P. Vaidyanathan and his colleagues. But here we're doing something very similar from only a single image, and we're getting the similar effect by introducing this convolutional beamforming. Now, since we now see that the performance is determined only by the sum co-array, that means that we can use sparse arrays that have a full sum co-array and therefore get very good performance using only a small number of elements. And in fact, we could reduce the number of elements down to a factor of a square root of n. So here we see the performance that we would get in ultrasound using delay and sum with 63 elements compared to a specific sparse array with 16 elements, and we see that the performance is exactly the same. I would like to end the talk by discussing briefly how one can combine models with learning. We're all aware of the fact that today a very popular approach across all data science areas are ideas based on learning that learn the information needed from large amounts of training data. With enough data, deep networks tend to learn almost everything and have led to the best results in various tasks like image recognition, speech translation, and more, which do not have good models. However, there's still many challenges with deep networks. In particular, we need very large training sets. It's very hard to interpret the results or to learn mechanisms using these results. Large data sets are needed for training, and it is very hard to say much about generalization and robustness. On the other hand, if we look at signal processing, in general, it is based on physical models. This allows us to easily incorporate domain knowledge and structure into our methods. It also allows us to perform inference with small data sets and to easily assess the quality of the output. The main drawback, however, of traditional signal processing is that it relies on accurate model knowledge, and in addition, inference can often be quite slow. So the question is whether we can combine the two, or whether we can combine the ideas of models and structure that we talked about until now into deep networks in order to get simple and efficient deep learning methods. So to see how we can do that, let's take a bird's eye view and signal processing versus deep learning. In standard signal processing methods, we usually have a set of measurements, which we'll call Y, and from them we want to infer some unknown that we'll call X. We typically have a model that relates Y and X, and we use that to design an algorithm that's going to determine X by optimizing some metric function, referred here to as F, and this will rely on the measurements and the known relationship. So typically this leads to a series of iterative steps that need to be carried out on the input to get the desired output. On the other hand, in deep learning, we replace the model by a black box that doesn't know anything about the problem. And what this black box now is going to do is it's going to get lots of inputs and paired outputs. And from them, it's going to learn the parameters or the weights in a series of layers. And this will form our deep network. We're then going to apply this learned network to a new input Y and hope that it will obtain a good recovery X. So to combine these two approaches, what we're going to suggest are two methods. The first is to integrate model-based methods into deep learning by relying on the idea of unfolding that was first suggested by Gregor and LeCun, and we've already seen some examples of this throughout the talk. The second is to do the reverse, to integrate deep networks into existing model-based algorithm. So this will give us the best of both worlds, but is done in slightly different ways, which depend on the application. So let's begin by looking at unfolding, which was first suggested by Gregor and LeCun and has gained growing interest in the community. So the idea on unfolding is to start with our metric that we want to optimize and write down an iterative algorithm to optimize that, which will typically lead to the following steps. We'll have some input processing, then some iterative step that we repeat, and then some final output processing. Now, the next thing we do is write out several of those iterative steps explicitly. So here we write out T iterations, let's say 10 iterations. We write them out explicitly. And then as the final step, we're going to use training data to optimize each one of these iterative steps and to find the unknown parameters directly from training data. So instead of assuming that the model is fixed in each of these iterative steps, we're going to learn the model parameters directly from data. So this leads to different unfolding algorithms, and those of you interested can see a recent review that we've written on these approaches together with Vishal Munga. So we've seen some applications of unfolding throughout the lecture, and I want to end by showing some further applications. So together with Vishal Munga, we've used this for blind deep learning, leading to a method we call DUBLID, deep unrolling for blind deep learning. And this leads to really good results, better than previously suggested networks for this problem. We've also applied this for super resolution, for example, in ultrasound, and you see again that it leads to very high resolution. We've used this for separating, for example, between tissue background and blood flow in ultrasound, and we did this by unfolding a network that's based on modeling the combined measurements as low-rank plus sparse. And in fact, this method was suggested in 2018, and at the time we referred to the method as Corona, Convolutional Robust Principal Component Analysis, and it appears that unfortunately this method went quite viral. So those of you interested in applications of unfolding to ultrasound, we have a recent review on deep learning for ultrasound where you can see more details about these techniques. Finally, the last approach we suggest is taking an existing model-based algorithm that is known to perform well and simply replacing any block that requires model parameters or is difficult to compute by a deep network. And we've applied these ideas to various problems in communication. For those of you interested, we have a recent review on this, and we also presented this in our tutorial yesterday. So one example we applied this to is for symbol decoding over unknown channels, where we based our deep network on the Viterbi algorithm, and this leads to what we call the Viterbi net, which has the same structure as a Viterbi decoder, but allows us to adapt to unknown channels by replacing the likelihood function by a learned likelihood function. We've also applied this to different factor graph methods, which rely on factor graphs and message passaging over the graph. And again, here we replaced the factor graph computation with a learned network when we don't know the channel statistics, and again apply this to symbol decoding in different communication networks. Finally, the last application I wanted to mention is to interference cancellation, which is very popular in multi-user MIMO. And here again, we could replace only the soft decoding step, which relies on channel statistic, by a learned decoding step, and this will give us the same overall behavior as successive interference, but allow us to adapt to unknown channels. So to conclude, we introduced a framework for interpretable, efficient, and high-resolution sensing by relying on exploiting structure in the problem and the actual processing task, taking both model-based and data-driven methods into account, and by performing joint optimization over all system components. We saw that this leads to new mathematical theories that provides bounds on sampling and resolution. We talked about new engineering developments leading to new technologies. And in the future, we hope that this combination of mathematics and engineering will lead to new scientific discoveries and new clinical methods by seeing information that we haven't seen before and by tracking effects faster than is possible today. So let me end by saying that I've skipped over many technical details. You could find them in our recent books and in the details on our webpage and some of our reviews on this topic. None of this would have been possible without the amazing team that I've had the privilege and honor to be working with, the students and engineers that I've been working with over the years. And of course, my amazing collaborators who have contributed greatly to this work, and many of the ideas, of course, were done together with them. So let me end by thanking you. Thank you very much for your attention.